Okay, hello everyone. So this is a problem with electrostatics that involves vector addition and subtraction. So we have three charges, Q1, Q2, Q3, like this, and point P in space here. We want to compute the net magnetic electric field at this point. All right. So first we choose our axis. We choose the origin at P. To the right is plus, and up is plus. And now we compute the magnitude, or sorry, the direction of the electric field at point P due to Q1, Q2, and Q3. So if we look at P, Q1 is a positive charge, so the field at P from Q1 is away from Q1. See, it's away from it, along the line joining them. So here's the line joining them, which is the y-axis. If we look at E3, E3 is negative. So the electric field is pointing towards Q3. So E3 is pointing towards Q3 along the line joining them. So it's at P3 pointing towards Q3 along the x-axis. And from Q2, which is positive, so at point P, the field from Q2 is away from Q2 along the line joining them. All right, we know the distance here is A and B are in nanometers, and here are the charges in coulombs. Okay. So first of all, we have to compute the magnitude of the electric field at point P to do that. Okay, we just drew them. Right now, I want to compute the magnitudes. Okay, so here is the picture again. I call this R1 because the way electric field is defined is K times the charge times K times the charge over distance squared, and distance is usually put as R. So here's R1, the distance between Q and the origin. So here is E sub 1, again magnitude. I want to talk about magnitude here. That means I'm gonna force myself to put positive numbers for Q1, Q2, and Q3. Although Q1 and Q2 are positive, so automatically the E1 will be positive. But for Q3, I have to force it whenever I plug numbers in. I have to plug in positive number for Q3. And the distance between R1 right here is B. This distance equals this distance, so I put B squared. E sub 2 is this distance, this electric field, and the distance between P and Q2 is called R2. I called it R2. And R2 now is the diagonal of this rectangle, or the hypotenuse of this triangle right here. So I can easily compute what R2 is. R2 is the square root of R1 squared plus A squared, but R1 is B, so square root of B squared plus A squared. So that's R2. Now when I square it, I remove the square root, and there it is. And the same thing for E3. Again, I gotta ensure what I plug in positive for Q3, and the distance between P and Q3 is A. So it's over A squared. Now, here is our situation isolated. So the first thing, now that we drew the vectors and wrote the magnitudes, break up or decompose any vector that is not fully along the x or y axis. E1 is along the y, E3 is along the y, E2 is not along either, so we need to break that up. So decompose E2 in our case, or our problem. This is the one that gets decomposed. So here's E2, here's the angle alpha with the x-axis. I get its projection along the y-axis, which is this one, and that will take the sine, because it's opposite to alpha. And then I get its projection along the x-axis, and that is the cosine. Now, I add and subtract along x and y according to my positive sense. My positive sense is to the right, positive in the x, and up, positive y. So I take E1 minus this E2 cosine alpha in the x. And now these two are added together because they are both pointing up. So now, if we assume that the net vector is called E and has an x and a y component, E sub x and E sub y, then E sub x is E3, which points to the right, minus E2 cosine alpha, which points to the left. And E sub y is E2 sine alpha plus E1, because they're both pointing in the same direction. So now I need to compute alpha. So I use just this triangle again, this being the square root of a squared plus b squared. That's a and that's b. Actually, I don't need to compute alpha. Alpha is not important. The sine of alpha and the cosine of alpha need to be computed, because the equations have sines and cosines of alpha, not alpha. So it's easy. Whenever I see a sine alpha, I substitute it with b over the square root of a squared plus b squared. Same for cosine alpha with an a on top. And now I write what Ex is. Again, it's E3 minus E2 cosine alpha. I plug them in here. This was the cosine alpha. Then I take out a Ka from both terms. That will make an a cubed down here instead of an a squared. And I put it in this form. And I do the same thing for Ey. For sine alpha, I plug in b over the square root. Of course, the square root has a power 1/2. I combine the powers here to get 3/2. Of course, I factor out a kb, and I induce a b cubed in the denominator here. At this point, this is all the analytical, theoretical, whatever you want to call it, done. I mean, this is it. This is the problem. All that remains now is plugging numbers in and getting answers. All right. So this is what I'm given. Again, I gotta remember now when I plug in Q3, I plug it in as a positive. I should have put a absolute value of Q3 here or something, but we need to keep that in mind. So here's E sub x. I put things in here. See, as you can see, for Q3, I plug in positive, and I got this. Again, it's just a calculator exercise. And when I plugged in for E sub y, I got almost the same number. So that tells me, I have close to a 45-degree angle right away. And here the force seems to be big because the charge is big. If we're talking, for example, about electrons, they have 10 to the negative 19 coulombs. Here it's 10 to the negative 9, so it's like 10 billion times more. It has more charge than the electron. Also, one thing that I want you to note is I didn't carry any units. I made sure that Q, all the Q's, are in coulombs. K is given in Newton meters squared per coulomb squared. And then all my distances are in meters. And that will ensure my electric field will come out as a Newton per coulomb. Okay? So pictorially, here is the Ex and Ey. They're both positive, so from point P right here, they both point one to the right, one up. And here's the resultant field E. So at P only feels this vector E right here. Doesn't know anything about the configuration. All it feels this. So what is that vector? It's the square root of the components summed up squared. Here it is. So 3.9 times 10 to the 17 newtons per coulombs. And then I computed the angle with the x-axis as tangent inverse with the absolute value Ex, Ey. And I got 46 degrees. as shown. Now this is a good way of writing the final result. You show the vector graphically, you give its magnitude, and then you show where the angle is that you compute it. Other ways of writing the vector are in ij notation. So E is EXI plus EYJ, and you could write it like this. Now I put the units at the end because they all have the same unit, so I could have put them in here or in here, but it becomes cumbersome. Over here is good. That's one way of doing it. I mean, you could put them here. Another way people like to write these vectors as parentheses, the components x and y. Again, here's the x, here's the y. I chose to put the units outside. You could have put them in here, up to you. You could also write them in a third way or fourth way as brackets right here. In this case, I put the units inside. I could have put it outside, but I just decided to put it inside. And that's basically it. This is the problem. Again, had some electromagnetics in it, electrostatics, which way the electric field points due to the presence of charges, and then adding and subtracting vectors by components. All right. Thanks for watching. See you in the next video.